Hello everyone, welcome to Reactify Labs. Today we will talk about Apache ZooKeeper. So what is ZooKeeper? ZooKeeper is kind of a coordination service. And why do we need a coordination service? And actually why specifically ZooKeeper or anything actually? So for that we need to understand what is the problem statement that we are trying to solve and uh, what role does zookeeper play in that. Okay, I have made another video on coordination services, but I thought let's make another one on one specific coordination service like zookeeper to actually show you how it actually works. Okay, the coordination services video was more about the concept of explaining why we need coordination services, what are the advantages and disadvantages of it, but this one is specifically using a coordination service, one coordination service. What are its technical implementations, what are the advantages of using this, what are the challenges associated with this, how do they make sure that the coordination happens among the nodes, what kind of algorithms do they use, what kind of internal technicalities are involved in this zookeeper. So for that I'm making this one dedicated video on one specific coordination service called zookeeper. Okay, so let's first discuss the structure that we are going to follow today. First we will talk about the introduction of zookeeper. Okay, next we will see the architecture of zookeeper. Next we will see the operations of zookeeper. After that the use cases, then advantages and challenges associated with zookeeper. Okay, now before we go with the introduction and all the technicalities of it, let's understand the problem statement that we are trying to solve first. Okay, so let's say you are making something called an Uber. Okay, you are making a ride sharing service like Uber. Okay, so your service, your ride sharing service Uber, needs to manage multiple components working together in a distributed manner, right? You will have multiple components, like you have to do a lot of things. First, driver matching. You have to do driver matching. You have to take care of ride requests. You have to take care of notifications, right? At a very simple level, let's say these are the three things. So driver matching means assigning drivers to riders. Ride requests means handling requests from the riders, like I am searching for the ride, I need to be taken care of. A driver who is searching for the rider, he needs to be taken care of. And then sending updates to drivers and riders, like okay, your rider is at this place, and the rider gets the message like your driver is arriving in 5 minutes, something like this. Okay, so each of these components might be running on different servers because they are different services. Driver, uh, Uber might have millions of drivers, right? So driver will have a different service, rider will have a different service. Okay, so if you see, if you log into your app, you will not be able to see any option to drive the Uber, right? Because they are on a different service. It's possible that they have a separate app for this. Okay, so each of these components might be running on different servers or clusters. They need to work together seamlessly, and coordination among them is crucial. Okay, there are some specific challenges associated with it, like service discovery. So how do different parts of the system find and communicate with each other? For example, the ride request service needs to know which driver matching service instances are available to send requests. So zookeeper, what it does is it provides a centralized service for maintaining configuration information, naming and synchronization. It can keep track of active service instances, allowing services to dynamically discover each other. Okay, another thing is, since it's coordination service, it means there are multiple nodes. So leader election. Suppose you have multiple instances of a service that need to coordinate as a single unit, like a service responsible for managing ride requests. You need one instance to act as the leader to make decisions or coordinate tasks. So Zookeeper can help with leader election, where services can use Zookeeper to agree on which instance should be the leader. This ensures only one instance is making decisions, preventing conflicts. Configuration management. If you need to update configurations like changing the maximum number of concurrent ride requests, how do you ensure that all instances get the update immediately? So Zookeeper can store configuration data in a centralized manner. Services can watch for changes and update their configurations in real time when Zookeeper notifies them of change. Okay. Distributed coordination also. Multiple services might need to work together in a coordinated fashion. such as ensuring that no two drivers are assigned to the same ride, right? Or managing access to shared resource. So ZooKeeper provides mechanisms for distributed synchronization such as locks and barriers. These can be used to coordinate activities across different services, ensuring consistency and avoiding conflicts. So in summary, if you see in this ride sharing example, ZooKeeper helps by providing service discovery to find available services, facilitating leader election to manage coordination among instances, managing configuration updates across distributed services, and enabling distributed coordination for tasks that need to be synchronized. So basically, ZooKeeper acts as a central point for managing these aspects, making it easier to build and maintain a robust and reliable distributed system. Okay. So now that we know the problem statement that ZooKeeper is going to solve, let's talk about the ZooKeeper. Okay. So let's start with introduction. So ZooKeeper is a distributed coordination service. ZooKeeper is a distributed coordination service that manages a large set of hosts. That manages a large set of hosts. It provides a reliable centralized service for maintaining configuration information. Okay. Core purpose of ZooKeeper. What is the core purpose of ZooKeeper? ZooKeeper is designed to coordinate distributed systems, ensuring multiple services can work together without conflicts, right? Multiple services can work together without conflicts. Okay. It's particularly useful in scenarios where nodes need to maintain consistency, such as leader election, configuration management, and distributed locking, right? So every node needs to know which one is the leader. Otherwise, everyone will declare itself as a leader, right? So ZooKeeper helps in these things. ZooKeeper is used for its ability to provide high availability and resilience in distributed systems. It ensures that even if some nodes fail, the overall system continues operating without data loss or inconsistency. Okay. Now let's talk about the architecture of ZooKeeper. Okay, there are a few terms which will come here. First is ensemble. So an ensemble is a group of ZooKeeper servers. A typical ensemble consists of 3, 5 or 7 servers to avoid split brain scenarios. Split brain scenarios as in, like, if you have, let's say, 2 nodes, what happens is one node can say something, other node can say something, right? But if you have odd number of nodes, what happens is this node will say either this or this. So at least one of them will get a consensus, right? So that's the advantage of using odd number of ensembles. Okay, either 3, 5 or 7. So a quorum is the minimum number of servers that must agree for a decision to be made, ensuring that ensemble can still make decisions even if some servers fail. For example, in a 5 node ensemble, at least 3 nodes must agree to commit a change. If only 2 nodes are operational, the ensemble cannot make any decision. Okay. Next comes ZooKeeper nodes. ZooKeeper nodes. The leader processes all write requests and ensures state changes are propagated to follower nodes. Followers serve read requests and replicate the leader's state changes. They also participate in leader election. Observers do not participate in quorum but serve read requests, helping scale through read throughput without affecting write performance. For example, imagine a distributed database system where ZooKeeper is used to manage configuration settings. The leader node is responsible for updating the configuration, and follower nodes ensure that all database instances have the same setting. Okay. Next is Z nodes. So Z nodes are data structures used by ZooKeeper to store its hierarchical namespace, similar to a file system's directory structure. Okay. So there are nodes which are just like the file system, something, these kinds of data structures will be there. Okay. So there are three types of Z nodes: persistent Z nodes, ephemeral Z nodes, and sequential Z nodes. So persistent Z nodes remain in ZooKeeper system until explicitly deleted. Ephemeral Z nodes are automatically deleted when the client that created them disconnects, often used for leader election and service registration. And sequential Z nodes have a sequence number appended to their name, providing a unique identifier reflecting the order of creation. Actually, Z nodes is a vast topic, so I will create a separate video on Z nodes. So please don't worry about it if you have not understood it. There are two things in this ZooKeeper actually which I need to talk about in separately. One is Z nodes and other is ZAP. Okay, it's a ZooKeeper coordination algorithm. Okay, so yeah, I'll not talk much details about these things now. Maybe next video will contain Z nodes and after that will contain ZAP, or next will contain ZAP and after that will contain Z nodes, something like that. Okay, but it will be right after this video. Okay, so clients can set watches. Actually, Z nodes have watches. Okay, actually ZooKeepers have watches. So clients can set watches on Z nodes to be notified of changes. In a distributed application, Z nodes can be used to store configuration data such as database connection strings. Clients can set watches on these Z nodes to receive updates whenever the configuration changes. Okay. Next is data model. Data model. So ZooKeeper uses a tree-like structure where each node is a Z node. The root is denoted by this, as we denote in our normal file system, and each child node is referenced by its path, such as let's say app, config, db. Okay, so means db is inside the config folder, which is inside the app folder. Okay, so each Z node has a stat structure including metadata like version numbers, creation time, and modification time. A microservice architecture might use a hierarchical namespace where services store all available services, and each service has its own Z node like services payment, services user. For example, like this, the services. Okay, this is like microservice. Okay, and each service has a Z node. For example, a payment service will be like services slash payment. Okay, similarly services slash user service. Okay, so this will be like this, a hierarchical order in which everything will be stored. Okay, next is sessions. A session represents a connection between a client and the ZooKeeper ensemble with a session ID, a timeout, and an ephemeral owner. Okay, session timeout determines when a client is considered disconnected. If ZooKeeper doesn't receive any heartbeat from the client within its timeout, the session is expired. In a distributed caching system, a client might use a session to register its presence. If the client disconnects, the session expires and the cache data related to that client can be safely invalidated. Okay. Next, let's talk about the ZooKeeper operations. First one is read and write operation. Okay. Also, before that, as I said, Z nodes I'll talk about later, and along with that, I also said something called ZAB. Okay, ZAB is basically a consensus algorithm, just like Raft. Okay, not like Raft is also a consensus algorithm. I have made a separate video on Raft. So ZAB is also another consensus algorithm which is specific to ZooKeeper. Okay, Raft is a general purpose algorithm, but this one is specific to ZooKeeper, which is actually ZooKeeper atomic broadcast. Okay, so I will make a separate video on this. Just wanted to clarify what ZAB is so that you have your expectations set. Okay, great. Now let's talk about read and write operations. So reads are served by any follower or observer node and are strongly consistent, but all writes are processed by the leader, ensuring replication to a quorum of followers before acknowledging the client. In a distributed key value store, reads could be served by any follower, but writes like updating a key's value must go through the leader to ensure consistency across the system. Okay. Next is watches and notifications. Watches and notifications. Setting a watch is important. Okay, clients can set watches on Z nodes to be notified of changes. Okay, there are different types of notifications. So node created. So it's triggered when a Z node is created. Okay, node deleted. It is triggered when a Z node is deleted. Node data changed. As the name suggests, it is triggered when the data of a Z node is modified. And node children changed. It is triggered when the children of a Z node are modified. Okay. So for example, in a service discovery system, a watch could be set on a Z node representing a service. If the service goes offline, triggering the deletion of its Z node, all clients watching that node would be notified and could switch to a backup service. Okay. Next is leader election. Leader election. So ZooKeeper uses ephemeral and sequential Z nodes for leader election. The node creating the smallest sequence number Z node becomes the leader. If the leader fails, followers elect a new leader based on existing sequence numbers. In a distributed database cluster, ZooKeeper might manage leader election to ensure only one node can serve write operations, avoiding conflicts. Okay. And next is sync operation. So the sync operation ensures a client sees the latest data. The client sends a sync request to the leader, which ensures all followers are up to date before responding. In a distributed logging system, the client might issue a sync before reading logs to ensure it gets the most recent entries. Okay. Let's see the use cases. I'm sorry. Let's see the use cases of ZooKeeper. So first one is configuration management. ZooKeeper stores configuration information for distributed applications. Clients can set watches on configuration nodes to automatically receive updates when configurations change. For example, in a cloud-based application, ZooKeeper might store database credentials. If the credentials are rotated, all instances of the application receive the updated credentials automatically. Next is service discovery. Service discovery. ZooKeeper enables dynamic service discovery by allowing services to register themselves as ephemeral nodes. Clients discover services by querying the appropriate Z node. For example, in a microservices architecture, services like authentication service and payment service could register with ZooKeeper. Okay, clients query ZooKeeper to find the current instances of these services. Next is distributed locking. ZooKeeper provides primitives for distributed locking, ensuring that only one client holds a lock at a time. In a distributed task scheduling system, ZooKeeper might be used to ensure that only one instance of a job scheduler runs at a time, avoiding duplicate job executions. Okay. Next is leader election. Leader election. ZooKeeper is widely used for leader election in distributed systems, ensuring only one leader is active at a time. And as I told you before, ZAB is used for this, ZooKeeper Atomic Broadcast. In a cluster of distributed caching nodes, ZooKeeper might manage leader election to determine which node should handle cache invalidation events. And next is queue management. Queue management. ZooKeeper manages queues where producers add tasks and consumers process them. Sequential Z nodes ensure tasks are processed in order. ZooKeeper implements barriers where processes wait until a certain condition is met before proceeding. For example, in a distributed image processing system, producers might add image processing tasks to a queue in ZooKeeper, and workers pick tasks sequentially to ensure they are processed in the correct order. Okay. Now let's talk about the advantages of ZooKeeper. First is high availability. ZooKeeper's quorum-based design ensures availability even if some nodes fail. In a distributed database cluster using ZooKeeper for configuration management, the system remains operational even if a few ZooKeeper nodes go offline, ensuring that cluster continues to function. Next is strong consistency. ZooKeeper ensures strong consistency across the ensemble, meaning all nodes agree on the system state. When updating shared configurations, ZooKeeper ensures that all nodes in a distributed system see the same configuration data, avoiding configuration drift. Next is scalability. ZooKeeper handles large-scale distributed systems with thousands of clients. Adding observer nodes helps scale read throughput without impacting write performance. For example, a large-scale microservices platform might use ZooKeeper to manage service discovery, with observer nodes handling the high volume of read requests from the various microservices. Next is simplicity. ZooKeeper provides simple, well-defined primitives for building complex distributed systems, reducing the burden on developers. Developers can use ZooKeeper's distributed locking mechanism instead of implementing their own, thus saving their time and ensuring correctness. Okay. And last is reliability. ZooKeeper's fault-tolerant design and automatic leader election ensures that the system remains reliable even during failures. For example, in a distributed payment processing system, ZooKeeper's leader election guarantees that only one node processes payments, thus avoiding double processing and ensuring reliability. Okay. Next, we will talk about the challenges associated with ZooKeeper. First is write scalability. Write scalability. Since ZooKeeper handles writes through the leader, write throughput is limited by the leader's capacity. In a high traffic distributed messaging system, the leader might become a bottleneck if too many write operations are directed to ZooKeeper for coordination. Okay. Next is latency sensitivity. Latency sensitivity. ZooKeeper's quorum-based operations can introduce latency, especially in geographically distributed ensembles. For example, a globally distributed application might experience higher latencies when coordinating with ZooKeeper due to the time required for quorum consensus across distant or distributed data centers. Okay. Next is complexity in configuration. Complexity in configuration. So properly configuring ZooKeeper for optimal performance can be complex, requiring careful tuning of parameters like session timeouts and ensemble size. For example, in a large-scale cloud deployment, improper ZooKeeper configuration might lead to frequent session expirations or unnecessary failovers, which affects the overall system performance. Next is split brain scenarios. Split brain scenarios. In certain failure cases, such as network partitions, ZooKeeper ensembles can experience split brain scenarios where what happens is multiple nodes believe they are the leader. Everybody is a self-proclaimed leader. So in a distributed file system like ZooKeeper, for coordination, split brain scenario, what it can do, it might lead to conflicting writes, okay, which causes data corruption, because since everybody is considering themselves as the leader and only the leader writes, so everybody will write, which is an issue, which is a challenge which needs to be addressed. Okay. Next is session timeout tuning. Session timeout tuning. So tuning session timeouts is critical to avoid unnecessary session expirations, which can cause ephemeral nodes to be deleted prematurely. In a distributed job scheduling system, improper session timeout tuning might lead to job scheduler nodes being incorrectly marked as offline, which disrupts the scheduling process. Okay. So yeah, this concludes the discussion on ZooKeeper. I could have extended this video to talk about ZAB and Z nodes, but that would make the video very long, maybe 1 hour long. and that would be too much. Okay, so let's what do we say in system design terms? Let's decouple the learning. Decouple the learning. Okay, so in this video we learned about ZooKeeper. In next video we will learn about znodes, and after that we will learn about zap. Okay, so yeah, that's all there was in this video. I hope this gives you a good understanding of ZooKeeper, its technicalities, its architecture, its advantages and challenges associated with it, what problem it is solving. And after 2 more videos, you will have better understanding and you will be in a position to talk about ZAB as well as znodes. So yeah, that's all there was which I had to talk about. Yep. Also, just one thing to point out: if again, if in the interview somebody asks you to make a system like this, or not like this, any big system where there are multiple microservices involved, where there needs to be coordination, there needs to be consistency. So you can talk about ZooKeeper there. You can talk about a coordination service. You can talk specifically about ZooKeeper, that you will use ZooKeeper to maintain the coordination. And if follow-up questions come in, like tell me more about ZooKeeper. What is something that we need to be aware of, or what is something we need to handle more cautiously when using ZooKeeper? What is something that ZooKeeper can do which other things cannot do? And most importantly, if like let's say the question comes like, why cannot we make our own coordination service? Why do we need to rely on ZooKeeper? It's because ZooKeeper specializes in these things. Okay, a developer should not need to worry about how to make a coordination service, because it's already made. We do not have to reinvent the wheel, right? If something is already there, we should use it. Okay, if it's really good, if it's popular, means it's proven, then we should use it. Okay, if let's say tomorrow you have to make your own ZooKeeper or make your own coordination service, then yes, you can do it. You can make your own coordination service if you think there are some flaws with ZooKeeper. But if you are making some other app, let's say a ride sharing app or a social media or social network app, then you should not focus on building a ZooKeeper or a coordination service. Your entire focus should be on making your own system better by using the existing systems or using the existing services that are there. Okay, so this is a very important thing to understand here. We should not make these things on our own. These are there, these are available, we should use them. Okay, so yeah, that's all there was which I had to say about this video. Thank you for watching. Please remember to like, share and subscribe. I will see you in the next one.